In this problem, we have two identical capacitors, and there are two different ways of connecting them. One possible connection is the parallel connection, that's the one on the left-hand side, and the other possible way to connect the two capacitors is the series connection, the one on the right-hand side. So we are going to look at some quantities such as energy, charge, and electric field for these two different types of connections. And in both cases, the group of capacitors is connected to the same potential difference V. First, let's look at the potential energy stored in each case and compare the two. Here's the potential energy formula. It's equal to 1 over 2 C equivalent times V squared. So the equivalent capacitance will be different for each group. However, V is the same for each. So then let's go ahead and calculate the equivalent capacitance for each group. For the parallel connection, the equivalent capacitance is simply the sum of each of the capacitance values. So that makes C plus C, which is equal to 2 times C. I'll use the superscript P for parallel. For the series connection, we add the reciprocals of the capacitance values and then we invert the result. So the series equivalent capacitance for the series connection is C divided by 2. Now let's substitute each of these values in the formula for potential energy. Here's the energy stored in the parallel connected group. The twos cancel, so we get U parallel is equal to CV squared. In the case of the series connection, we get an extra factor of 2 in the denominator, so that makes CV squared over 4 for the energy stored in the group connected in series. Now we can divide these equations side by side to see how the two values are connected. So then UP divided by US is equal to 4. That makes UP equals 4 times US. So the energy stored in the parallel group is 4 times as large as the energy stored in the series group. Now let's calculate the total charge stored in each case. In general, for any given capacitor, charge is equal to capacitance times voltage across the terminals of the capacitor. So on the parallel connection, each capacitor has voltage V across its terminals. So we have C times V stored in each capacitor in this case. So QQC times V for each of these. In the series connection, on the other hand, the total voltage V is shared between the two capacitors. Because they're identical, each capacitor will have a voltage of V over 2. And then the charge stored in each one is then going to be equal to C times V over 2. So Q equals C times V over 2 for each capacitor in the series connection. The total charge for the parallel case is going to be equal to 2 times CV, each capacitor having a charge equal to C times V. And in the series case, the total charge is going to be equal to 2 times CV over 2, again CV over 2 being the charge stored in a single capacitor in the series connection. Again, we can divide these two equations side by side to find how the two quantities are related. We get QP divided by QS equals 2, so then QP equals 2 times QS. Total charge stored in the parallel case is 2 times as large as the total charge stored in the series case. Next, we'll compare the electric field for each connection type. Now, let's again use the fact that the potential difference across the capacitors in the parallel connection is equal to V. And remember, the electric field is equal to potential difference divided by the plate separation for parallel plate capacitor. So here we're going to have E equals V divided by D, D being the plate separation. These are all identical capacitors, so all have the same plate separation D. In the series case, on the other hand, the potential difference between across each capacitor is V over 2, so then we get electric field magnitude equals V over 2 divided by D. So that makes V divided by 2D. So we have half as much electric field strength here. So this is electric field in the parallel connection, electric field in the series connection. Again, if you divide the two equations side by side, you get electric field magnitude in the parallel connection is equal to 2 times as large as the electric field magnitude in the series connection.